Hi everyone, I'm Marco Mancastroppa, a third-year PhD student in physics at the University of Parma. And first of all, I would like to thank the organizers for the opportunity to present my work as a video poster. Uh, I will show our results on the effects of stochastic sampling and heterogeneities in the control of epidemic processes. And this is a joint work with Alessandro Bezzani, Raffaello Burione, and Claudio Castellano. Temporal networks are models for systems of many elements which interact through interactions that are not fixed in time but evolves over time. In particular, they are made up of nodes which are connected to each other through links that are created and destroyed over time, producing atemporal dynamics. Clearly, these kind of networks are able to model several systems with physical interactions, but we are interested in the consideration of a dynamical process occurring on top of it. Indeed, when the time scale of the dynamical process and the network evolution are comparable, we cannot neglect the network dynamics, and the network dynamics itself is able to produce some effects on the dynamical process occurring on top of it. And we would like to understand the effects of network dynamics on dynamical process, and to do so, we focus on epidemic processes. Indeed, an epidemics is a stochastic process which occur on the network of human interactions, and in particular, we can estimate the effects of the network evolution on the diffusion process by focusing on the phase transition of epidemic model. Indeed, epidemic models such as the SIR model feature a phase transition between an absorbing phase in which the epidemic do not spread and an active phase in which the epidemic do spread, infecting a finite fraction of the population. The phase transition is characterized by the control parameters, that is the effective infection rate, and is the ratio between the infection probability and the recovery rate, and its critical value is the epidemic threshold. The value of the epidemic threshold has been studied for static networks for the several epidemic models, such as the SIS model, observing that the topology of the network affect the epidemic spreading and the epidemic threshold. But for temporal networks, the situation is more complex because the adjacency matrix of the network evolves over time. So we cannot say that the epidemic threshold is linked simply to one snapshot of the adjacency matrix, but it depends on the way the adjacency matrix evolves in time. And this means that the epidemic threshold depends both on the structure of the network and on its temporal evolution. And this is quite important because if the network dynamics affects the dynamical process occurring on top of it, can happen that the dynamical process induce some modification in the network evolution. And this is the case of epidemics, in which containment and control measures induce adaptive behavior in the population, which change the way the network evolves in time, and so the epidemic spread itself. And this is the case, for example, of lockdown, which was essentially aiming to stop the link formation, to stop the epidemic spreading, or also contact tracing. Contact tracing dynamics is based on the idea to break the chain of contagion without stopping the link formation. And it is clear that contact tracing dynamics is much more complex to be modeled because of the fact that we have three dynamics coupled that are the network evolution, the epidemic processes, and the contact tracing process. And in particular, the contact tracing process evolves as a contact exploration over the interaction dynamics. And the idea of this work was that to compare manual and digital contact tracing that are due to contact tracing protocols proposed, comparing their effectiveness in increasing the epidemic threshold. Indeed, manual contact tracing is based essentially on interview by medical staff who contact an index case and try to reconstruct all the contacts of him and he will remember essentially with probability epsilon each contact that he had engaged in the past. And obviously, this approach is characterized by delay in tracing and isolation. While on the other side, we have digital contact tracing, which is based essentially on the download of an app, of a tracing app, which happens with probability F, and there are no delay in tracing and isolation. But when comparing manual and digital contact tracing, typically all focus on this difference in the timing of isolation. However, there is a main and big difference between the two contact tracing protocols that consists in the way they sample the contacts and they explore the contacts. Indeed, manual contact tracing performs a stochastic sampling with an annealed configuration. Indeed, all links are traceable and can be traced. All nodes can be traced, and simply the contact tracing is activated by the network evolution and the epidemic evolution. While digital contact tracing is performed only on through localized sampling, since the sampling and the contact tracing can happen only on a link between a couple of nodes who downloaded the app. So we are in a quenched configuration because the network and epidemics evolution induce contact tracing, but it can only happen on a link that are already fixed at the beginning of the epidemics. And so if we fix the same probability to trace a contact for manual and digital contact tracing, if we have an infected individual who infects a susceptible node, the probability to trace the node and the contact is the same. But if the same node infects two susceptible individuals, the probability to trace the node will be always higher for manual contact tracing compared to digital contact tracing. Obviously, to state this aspect and the fact that the intrinsic difference in contact exploration makes manual contact tracing more effective than digital one, we need to construct a complete model with a network evolution and epidemic process and study the effects on the epidemic threshold. So we consider the activity-driven network, a network in which at each node we assign two parameters that are the activity and attractiveness. The activity of a node sets its activation rate. The node activates with a Pearsonian dynamics. And when he is active, he will engage a link with another node. And the other node is chosen with probability proportional to its attractiveness. The activity and attractiveness are typically power law distributed with heterogeneities. And this means that there are a lot of hubs and nodes with very high number of contacts, which means that they behave like super spreader in the epidemics. On this kind of network, we consider an epidemic model which emulate the main stages in clinical progression of COVID-19. In particular, susceptible node infected can become symptomatic or asymptomatic. Asymptomatic nodes will always be contagious unless they are traced, while symptomatic individuals typically stay pre-symptomatic for a period of time in which they are contagious, and then when develop symptoms, they will be isolated and they will activate contact tracing on their contacts. In particular, contact tracing is implemented through the introduction of two other compartments, and in manual contact tracing, the symptomatic individuals will recall all its contacts with the probability epsilon, each of them with probability epsilon, and eventually we'll have a delay in the isolation, while digital contact tracing is activated only if the symptomatic node has downloaded the app, and he will remember with probability 1 all the contacts that he had engaged in the past, only with those who downloaded the app. And the tracing is instantaneous. So finally, to obtain the epidemic threshold, we write down the mean field equation of the model, which are exact since the model is completely mean field. The equations are quite complex, but they can be linearized around the absorbing state, and they apply in a linear stability analysis, we obtain the epidemic threshold. And the relation for the epidemic threshold are those you can see on the screen. They are quite complex, but they are quite general because they are true for arbitrary distribution of the activity and distribution of the app in the population. They can be solved numerically, And for example, if we consider the most simplest case of an homogeneous population, we can obtain an explicit form for the threshold in the manual and digital contact tracing, and we can compare their effects in increasing the epidemic threshold. Indeed, we observe that digital contact tracing increased the epidemic threshold much more than the digital one, and this also considering the same probability to trace a contact, and this confirms the fact that intrinsic difference in contact exploration favor manual over digital contact tracing. Moreover, if we add heterogeneities, so the presence of super spreaders, we observe that the differences are amplified and manual contact tracing is extremely more effective than digital one. And this is because a super spreader who do not download the app will never be traced digitally, and so it will carry on infecting a lot of people, while in the manual contact tracing, it will be traced very easily because of the high number of contacts it had engaged in the past. So finally, if we consider also a more realistic scenario with a delay in manual contact tracing or limited scalability, we can observe that again, manual contact tracing is more effective unless we consider very long delay and very high app adoption level. Also, in hybrid contact tracing protocol, we can compare the effectiveness of manual and digital contact tracing when they are combined in hybrid protocols. And again, we can see that manual contact tracing need to play a prominent role because its effect is much more strong compared to that one of digital contact tracing. So concluding, we propose an epidemic model for epidemic spreading on temporal networks with contact tracing. We compare manual and digital contact tracing, and we show that manual contact tracing, due to the way it performs contact sampling, performs always better than digital contact tracing, and also in hybrid protocols, manual contact tracing play a dominant role. Further perspectives are in the direction of an integration of protocols and multiple-step contact tracing. And thank you for the attention.